Welcome back. In today's lecture, we will discuss the separation of boundary layers from the surface and about the drag on bodies moving in fluids. We had seen that in creeping flows, which are flows at Reynolds number much below 1, the characteristic pressure difference is of the same order as the characteristic shear stress. The drag on this sphere is given by 6 pi mu r u Stokes formula, of which 2 pi mu r u is because of the shear stresses on the surface and 4 pi mu r u is because of the pressure differences. The pressure is antisymmetric. The pressure at the nose of the body is positive. The pressure at the tail of the body is negative. Note that the drag on a sphere or any other body in a low Reynolds number flow does not depend on the density of the fluid. This agrees with the approximation of negligible inertial forces at very low Reynolds number. However, the conventional practice, largely dictated by the fact that most flows of engineering interest are at fairly large Reynolds number, uses inertial force 1/2 rho u square as the characteristic pressure difference and define the drag coefficient CD as drag divided by 1/2 rho u square times the characteristic area. From the dimensional analysis, we can get CD is a function of Reynolds number and the geometry. If we plot the drag coefficient versus Reynolds number, we see that the drag number decreases with Reynolds number, but at very high Reynolds number, the drag coefficient is almost constant of the order 1. In fact, its value is about 0.5. Initially, the drag varies linearly with velocity, but for larger value of Reynolds number, the drag varies like u square, since the drag coefficient is about constant. But the point to notice is that the drag at large Reynolds number, the drag coefficient is of order 1. This seems to be in contradiction with the approximations that we have learned to make. D'Alembert proved that for incompressible and inviscid potential flows, the drag force is identically 0 on a body moving with constant velocity relative to a fluid. This happens because in the inviscid flow, as the fluid accelerates from the stagnation point at the nose to shoulder, the pressure decreases. On the lee part of the body, the velocity decreases to the stagnation point and the pressure rises. Thus, the net force on the right, on the front part of the body, is being cancelled exactly by the forward force on the lee side, resulting in 0 drag, 0 pressure drag. Of course, there is no shear stresses, so there is no shear drag. It was proved later that this drag is 0 on all bodies, whatever be the shape, not necessarily cylindrical or spherical. Now, this result was obtained for non-viscous flows. In actual flows at high Reynolds number, where we have shown that we can neglect viscous stresses, the drag is not 0. And it is not surprising that it is not zero because we are neglecting viscosity. So, in the presence of viscosity, there would be viscous drags, viscous stresses, and hence the presence of drag would not be surprising. But since in such flows the viscous forces are small compared to inertial and pressure forces, the drag must be small compared to pressure forces, or the drag coefficient defined with pressure difference as the characteristic stress should really be small. Zero drag predicted by D'Alembert is therefore in direct contradiction to the observation of drag coefficient order 1 on bodies moving relative to the fluid. It is further confusing when we note that the drag coefficient on a flat plate derived with the boundary layer approximation is about 1.328 divided by Reynolds number under the root, which again is quite small and in line of what is expected because of the approximation. So, the real D'Alembert paradox is not that there is a drag, but that the drag on a blood body is large, not of the order of shear stresses, but of the order of pressure forces. The resolution of this paradox lies in the peculiar dynamics of the boundary layer. That is, in its tendency to become reversed under certain conditions and to separate from the wall. This is accompanied by formation of eddies in the wake of the body. We had seen that flow behind a cylinder looks like this. This changes the pressure distribution on the wall from the inviscid one and leads to incomplete recovery of pressure in the wake, leading to drag forces of the same order as pressure forces. Thus, the separation of the boundary layer on the surface of a body makes the flow disturbed and the pressure does not recover back to its original level in the wake of the body, and thus a pressure drag results. Thus, the drag coefficient defined the way it is of order 1. The separation occurs in all kinds of geometries, including internal flows. Flow through blades of rotary compressor and turbines are also victim of the problems caused by separation if not designed properly. Designing bodies with low drag or internal passages with small losses are attempts at suppressing separation. Consider this two-dimensional body. The flow about this separates at these 2 points. And this separation is because of a flow reversal on the surface of the cylinder. And this causes the formation of eddies in the wake. The actual flow about such a body looks like this, separating from the surface. This is another picture of a boundary layer separating from a body. This flow is made visible by applying a coat of titanium tetrachloride on the surface of the body, and when the air flows past this, it produces a smoke-like vapor, and we can see how the vapor separates from the body and creates vortices in the wake. We have seen earlier that in inviscid flow, the pressure distribution is given by this curve. The pressure coefficient is 1 at the nose. It goes down to value of -3 at theta is equal to pi by 2, which is at the top of the cylinder. And in the rear of the cylinder, the pressure coefficient is again 0.1. The pressure distribution is completely symmetrical fore and aft, and so the total drag is 0. But because the boundary layer that forms on the cylinder separates from the body, this pressure distribution changes in the rear, though in the front of the cylinder it remains as if the flow is inviscid. So in an actual flow with high Reynolds number, the pressure distribution is more like this. On the graph, it is like this. So pressure in the wake has not recovered to the value in front of the cylinder, and this results in considerable drag. Since this drag force is because of pressure forces, when the drag coefficient is normalized with respect to pressure forces, we get a value of the order 1. We show here how the velocity profile changes down a surface where the pressure is increasing in the streamwise direction. Because the flow in the boundary layer has slowed down, so the kinetic energy of the flow here within the boundary layer is much less than the kinetic energy in the main flow, that is the flow outside the boundary layer. And if the flow outside the boundary layer has sufficient energy to negotiate the adverse pressure gradient, the flow within the boundary layer does not have sufficient energy. And so the flow within the boundary layer near the wall slows down much more. Still later, the flow velocity near the surface has a 0 slope. du by dn tends to 0 at the surface. The fluid in the boundary layer close to the plate, not exactly at the plate, but close to the plate, is turning to be about 0. And a little later, because of more increasing pressure, the flow reverses. The flow starts flowing in the backward direction near the plate. Because of this, a separation occurs, and we get this as the line of separation. There is a reversed flow within the boundary layer or close to the surface. So the boundary layer that was for developing here now separates and moves this. This whole region here now is disturbed. The pressure here is no longer equal to the pressure that would have been if the flow was truly inviscid and no boundary layer was forming. Since an increasing pressure, that is dP by dx positive, leads to separation, which is not a desirable condition, such a pressure difference is called an adverse pressure gradient. And wherever the pressure gradient is negative, that is, pressure is decreasing in the streamwise direction, we call that favorable pressure gradient. We show here the typical velocity profiles and the shear stress profiles in flows with negative pressure gradient, that is favorable pressure gradient, and in adverse pressure gradient. The shear stress here becomes 0 because du by dy is 0. In this case, du by dy is positive. There is positive shear stress. Separation occurs wherever there is an adverse pressure gradient. If we have a cylinder and a flow past this, there is separation here, because if the flow was inviscid, the pressure would have been increasing after that. And so the separation takes place a little before the shoulder points. Now, if we attach a splitter plate to the cylinder, a plate in front of the cylinder, then the flow taking place in that direction, the velocity is decreasing and pressure is increasing. And the presence of this plate causes a boundary layer to develop here, and this boundary layer would separate in the presence of this adverse pressure gradient. Thus, we have the flow which is separating somewhere here on the two sides. And we have vortices formed here in which the fluid is recirculating in top. This did not happen when there was no plate, because though the pressure was increasing, there was no wall on which a boundary layer was developing. Similarly, we have this plate held perpendicular to the flow. The flow separates at this tip, because if the flow was to proceed down the back side of the plate, the pressure would have been increasing, and the flow separates, forming two large attached vortices. Because the Reynolds number is not very high, if the Reynolds number was very high, these vortices would have been washed down, and we would have a region of turbulence in that place. Here, we have flow in a diverging passage. The divergent angle is very large. We have, this is the flow of water through the diverging passage. There is an electrical wire here in which we are passing a current so that the hydrogen bubbles are being formed. You notice that near the wall, the flow is backwards. The hydrogen bubbles formed here are going back and then being washing down. So the flow has separated at somewhere these locations. The passage is diverging, air is increasing, velocity is decreasing, pressure is increasing, adverse pressure gradient. Presence of wall, boundary layer is developing. So the boundary layer separates in the presence of adverse pressure gradient. This is why the divergent portion of nozzles, known as diffusers, should be designed with very small divergence angle, so that the adverse pressure gradient is not too much, not that causes separation. This sketch illustrates the separation that we are talking of. At about this point, the velocity gradient normal to the wall decreases to 0 and the flow separates. We have thus separation at these two locations, and there is a reversed flow near the wall, as you can see. We have recirculating eddies in this region. Separation also takes place on aerofoils if the aerofoils are at large angle of attack. In this case, we have shown a small angle of attack. A boundary layer that developing on the upper surface is shown here by smoke streak lines. When we increase the angle, if the flow was to go around this, then the pressure would increase. And so it creates an adverse pressure gradient very close to the nose, and the flow separates itself from the wall at the nose itself. This is stall in the language of avionics and needs to be avoided. This leads to sudden decrease in lift and a sharp increase in drag, a condition quite harmful for the aircraft.